sponsored by Incogni. This high-powered rocket is designed to reach Mach 3, but there's something special about it. It's these fin tabs at the back. These are control surfaces to guide the vehicle in yaw, pitch, and roll. Without these tabs, the rocket spins around like this. I started controlling the roll axis of my high-powered rockets about a year ago. This technique improves the footage during flight quite a lot, but if we add in pitch and yaw control, we can reduce the recovery dispersion, that is, how far the rocket drifts from launch to landing. In a previous video, I built the booster section for this rocket with servos embedded into the carbon fiber fins, and today we're going to talk about the guidance package that controls those servos. Guidance is controlled by the AVA flight computer, which stands for All Vehicle Avionics. I designed this schematic in PCB in 2020. AVA is housed inside the guidance package, which also holds the telemetry radio, a GPS antenna, 3 GoPro Hero 10 cameras, and a VGA cable to connect the AVA flight computer to the servos. Yes, that VGA, the design standard set in 1987. The same cable made to connect this computer to this screen. Listen, hear me out. The guidance package connects to the 4 servos, and each servo uses 3 pins to control it: signal, 8.4 volts, and ground. A VGA cable, or technically an HD15 cable, gives us 16 separate lines to work with. But Joe, I hear you say, that's way too many pins. Fret not, my sweet little chickadees. I have a plan. The servos are MKS 6160s, real beefy boys. The stall current at 8.2 volts is 2.5 amps, and that's what we'll be designing around. The wires inside this VGA cable are gauge 26, so they can carry about 3 amps, but we do need to think about the connector too. A rocket is a high vibration environment, which means that cheap connectors like this aren't always going to be reliable, so let's double up. We'll use 4 pins for power and 4 for ground, then combine them at either end so intermittent connectivity gets spread out. That means with 8 pins for power and ground, the next 4 can go to the PWM signal, bringing us up to 12 used pins. But Joe, I hear you scream, what about the high vibration environment? If a pin disconnects momentarily, it could mean catastrophe for the flight. You're so smart. You know that? Great thinking. Since we've used 12 out of the 16 pins, we have an extra 4, and so what we'll do is we'll double up that PWM signal to the last 4. These last 4 are just duplicates for the servo signal lines, and with that, we have a connection to the booster section with some redundancy. I need this connection to break at apogee. That's why we're doing all of this. The drogue parachute is stored in here, so at the peak of flight, all 16 lines to the servos at the aft of the airframe need to be broken cleanly, and VGA cables happen to be cheap, redundant, and just the right amount of force to pull apart. I love how that feels. The avionics bay is made from this section of carbon fiber coupler tube. In the center, I'm placing a little bit of fiberglass as a switch band. This fiberglass segment needs to be full diameter with the rest of the body, and so in addition to chopping it up to the right length, we're going to lay up some of this biaxial fiberglass sleeve on the outside. This mildly increases the strength, but it's mostly about keeping the outer diameter consistent. If you're new here, you might wonder, why is he wearing a respirator? And that's because I can't shut the heck up about safety. Essentially, anytime I'm modifying the shape of something that is made out of fiberglass or carbon fiber, dust gets in the air. If you want to see this for yourself, next time you work with fiberglass or carbon fiber, buy a high-powered flashlight and point it up into the air. The backlighting will allow you to see those dust particles much more clearly. These particles are so lightweight that they can hang in the air for hours, and I like to think of that amount of time as sort of a cool down time. Running an air handler in your shop or garage can help reduce this cool down time. But when in doubt, I just toss that respirator on. And also, I don't know what kind of vapors are coming out of this expired epoxy. I covered the upper parachute section and the coupler switch band in this biaxial sleeve, and I should have done this all as one tube. While the parachute section worked fine, the switch band was short enough that I had issues with the edges delaminating, and had I done this with a longer tube, I could have cut off the correct length of segment later. While the epoxy was still green, which means not quite cured, I was able to take a knife and trim off some of the excess. When I attempted to clean up the edges on the lathe after, I had this moment of genius. The part wasn't secure enough on the lathe, and as a result, when the tool dug in, it delaminated a bunch of the biaxial weave. As evidenced by this horrific seam, the part is thin enough that the lathe bends it when it goes in there. So all of this is to say, I really should have done this as a much bigger section and then cut off the final length afterward. Doing a part this small with this sleeve layup just didn't work that well. As previously mentioned, this is a non-structural part, so good news, we can just send it. After prepping both sections, I epoxied the switch band onto the carbon fiber section using Loctite E120HP. These parts came out just a little bit lopsided, so I marked the clocking that seemed to fit best with this silver Sharpie here. And after trying to sand down some of those imperfections and that horrifying seam from the lathe, it's time to make the camera cutouts. The cameras we're using for this rocket are GoPro Hero 10s, and if this doesn't look like a GoPro for you, it sounds like I have a video for you to watch. These cameras start out in a more typical form factor, then I cut them open with a Dremel, remove all the unnecessary bits, swap out a ribbon cable, remove some thermal tape, add an SD card extension, thermal paste the crap out of the internal electronics, and then attach about 30 grams of aluminum as a heatsink. This fixes the primary issue with this camera, which is that when recording at 4K 120 FPS, the recording time is somewhere around 4 minutes before the camera overheats. But with this aluminum block, that number goes up to 45. The whole assembly is potted in 5-minute epoxy to protect it, and then it gets epoxied inside the avionics bay. Each camera gets attached to about 2 feet of PWM extension cable, and this will serve as the power, ground, and shutter signal for the camera. The shutter is just the record button. When it's time for the GoPros to record, Ava just pulls that button to ground for about a half a second, and we're good. Like I said before, there are 3 cameras on this rocket. One of them is going to look up, the other one's going to look down, and the third is going to look out at the horizon. The up and down cameras are going to stick out into the airstream at speeds up to Mach 3. And as you watch this time-lapse, you might be thinking, Joe, there's no way you're going to use a PLA shroud on this, right? Well, first of all, do not hate on PLA. We will get there in like 1 or 2 videos, but it can survive those speeds. But second, these are to help us create the shrouds around the lenses. While the body of the GoPro gets epoxied inside, the sensor element gets epoxied outside. I pin all these things down using CA and a little bit of accelerant to set them in place, and then the epoxy is going to pot them in place more structurally. This is how I epoxy the cameras inside as well. They're pinned in place using a little bit of CA and a little bit of 5-minute epoxy. Then once that cures, we pot the whole thing in much more. This is a rather inelegant solution, but we are going to fly this rocket multiple times, so I'm getting good use out of the cameras. For larger diameter rockets, it'll be much easier to design custom fixtures that allow us to hold the cameras in there and then take them out and reuse them another time. But on small rockets like the Meat rocket, I mean, listen, the Meat rocket's 4 inches. That's a lot of inches. That's plenty big. 4 inches is like a lot. But on vehicles that size, it's a little easier to epoxy these things in place. Really, the most annoying part about this process for me is how long it takes for each epoxy operation to cure. What I like to do is set up a space heater to help accelerate that process. The hotter the epoxy is, the faster it will kick and then cure, and then the faster I can move on to the next step. After locking the up-looking and down-looking cameras in place, I made the hole for the horizon camera. I did this first by drilling a large pilot hole and then dremeling out the remainder. This camera was more difficult to secure in place because it had to be mounted on that lens. I did this using a decent amount of 5-minute epoxy, and one of the great things about this stuff is how gummy it gets for a little while. The epoxy doesn't immediately cure. It gets harder and harder and then eventually turns into like a really hard jello. And while I had covered the lenses with blue tape for all of this process to make sure I protected them, the gelled up 5-minute epoxy peeled away perfectly for the horizon camera. Alright, time to change gears. In addition to housing cameras, the switch band also contains 2 power switches. One of these powers on almost the entire guidance package, and the other one powers on the servos. This is a safety decision. Adding active control on a rocket like this is dangerous. It's a high-risk activity. If I arrive at the launch site and something seems off, the rocket doesn't seem happy, maybe one of the fin tabs doesn't look like it's actuating all the way, all I have to do to fly this rocket without guidance is flip that switch. It cuts power only to the servos, so the rest of the rocket can fly normally, and we have enough stability margin in our simulation to tolerate that. This is a topic for another video, but just to state it here, active control in high-powered rocketry is a high-risk activity. You should only be doing it if you are really certain that your system is going to perform well. With rockets like this, go fever is a hell of a drug. There's so many months of work put into this project, and if I get to the launch pad and something doesn't look right, I'm going to feel that urge to fly it anyway. And so if I give myself a metaphorical exit off of the highway by turning the power off to the servos if I'm not feeling 100% confident, that's a great way to do this responsibly. If you're going to do active control in high-powered rocketry, please make sure you do it responsibly. Simulate the flight heavily, and give yourself an opportunity to de-scope or detach control surfaces right beforehand. The wire harnessing on this build is far from my best work. While every connection is shrink-wrapped and insulated, and I have no doubt that it will actually work in flight, it's just not that elegant. Much like the cameras, this is a problem that gets easier with scale. For rockets like the Space Shot, I won't need these cables to carry meaningfully more current, so the wires can stay the same size while the volume inside grows exponentially, thanks to the square cube law. After dry fitting the servo connection point to Ava, I was able to test continuity through the VGA connector to confirm that everything looked good. And once this cable harness is done, it's time to mount those power switches. Like most things on this rocket, these are getting epoxied in. They only need to go in once, and they shouldn't need any service. That's such a dangerous sentence. The switches have been fine. It's not foreshadowing. They're totally fine. These little guys are from a company called FingerTech Robotics, and they're meant for combat robots, which means they can carry an insane amount of current. They use a hex key to turn them on or off, and I'm going to pot them in place using a little bit of CA and then 5-minute epoxy. When drilling the holes for these switches, I was a little worried about damaging the cameras on the inside, and this is one of the best things about a drill press. You can use the depth stop. You can use the depth stop, the depth stop adjustment. It doesn't even say adjustment. Adjust me? What? Am I having a stroke? I might be having a stroke. You can use the depth stop adjust me to stop. You can use the depth stop adjustment to set the lowest height you want your drill bit to go to. So if I'm worried about drilling into the sensitive camera components, I can set that adjustment here so that I know I'll never touch them. Just like the Horizon camera, when that 5-minute epoxy leaked through a little bit, it was very easy to peel it off while it was still gummy. And now I'd like to tell you a little bit about power. Power is what happens when you have more hot glue sticks than anyone. Power is needed quite a lot within the guidance package. Each GoPro draws about 750 milliamps depending on the voltage. Rounding up for safety, that's 2.4 amps of current draw. The RFD900 radios I use can draw about 1 amp maximum, but they don't draw that continuously, so we'll round down to about 500 milliamps of draw. Rounding up a bit, Ava draws an extra 100 milliamps, and as I said earlier, we're speccing around the stall current of all 4 servos. That stall current at 8.2 volts is 2.5 amps, totaling 10 amps of stall current from the servos. If we're being generous and assuming the worst case scenario, this brings our intermittent draw up to about 12 or 13 amps. This is the current draw in flight, which is only going to last at most maybe 10-15 minutes. Once again, being very generous and speccing for the absolute maximum current draw, this means we need about 3.3 amp hours of capacity in the battery. But that does not account for the time that the rocket's going to be sitting on the pad idling, and this is foreshadowing. Hypothetically, if I were to have some type of technical issue on launch day, hypothetically, I would want to have a very large battery reserve so that power wasn't the thing constraining us. And hypothetically, if I wanted several hours of pad-on idle time to troubleshoot these issues, I'd want to not worry about that power. This goes without saying, but all of this is hypothetical. I never have any issues with the rockets I build. The battery I selected is 8,000 milliamp hours with a 100C rating for current draw. This very generously fits our spec, but it's a little bit too big to fit in the avionics bay, so I broke it open. This is one of those really hardened batteries, which I definitely paid a little extra money for, and then I immediately threw that money in the trash by just breaking it to bits, and just like the cameras, the battery was epoxied into the avionics bay. The reason this epoxy looks so gross is because it's filled with Kevlar pulp. The E120HP stuff that I really like using is just a little bit too thin for my application, and so in settings where I needed to hold its shape immediately, I loaded up with Kevlar pulp. Around this time, I also covered the GoPro lenses in epoxy. This stuff is filled with West System 410 filler, which I'm really enjoying using. I got this tip from my buddy Braden over at Rocket Vlogs, and because it's a proper fairing compound, as opposed to the thermocells I was using before, this means it sands away really easily. So while I try to get a good initial shape with this epoxy, it's really easy to sand it down to a much prettier shape at the end. Next up, this avionics bay is sealed off on either side to protect the components within, and that's done using bulkheads. We're going to make these bulkheads out of the same carbon fiber that I used to make the fins. This is that half-inch thick, quasi-isotropic stuff, which is so unbelievably overkill for the task at hand, but it's the stuff I have. Oftentimes, if you see me make a decision that seems strange in material choice or tool choice, it's because that's the stuff that I have access to at the time, and also it's a little bit the brainworms for sure. I'm cutting these bulkheads out on the Carbide 3D Shapeoko 5 Pro, and I'm using the dust boot to collect as much of that carbon fiber dust as I can. That's going into a shop vac with a HEPA filter inside, and yet even still, I also wear a respirator during this. I sound like a broken record, but carbon fiber's no joke, and you gotta protect those lungs. While we're cutting these out, can I tell you something really stupid? So when I cut out the fins for the booster section, I used a carbide end mill, but this is not really the right tool for the job. When you're cutting composites, something that's diamond coated would be a little bit better. These are very expensive tools, but they'd prevent the ripping that happens with the carbide end mill on these fins. I bought some of these diamond coated carbide end mills to make these fins, but they arrived too late for me to use them. I cut out these bulkheads like a month or two later, even while I had the diamond coated carbide end mill, but I was too lazy to put it in the CNC, and so I just plowed the regular carbide through it, and it ripped the whole way. There's no reasoning behind this decision other than that I was lazy and didn't want to change the tool, and it still cut them out just fine. I just find it very funny that I purchased the right tool and still chose to use the wrong one. I'm cutting out 3 of these bulkheads. One of them is going to be the lower section of the guidance package, one is the upper section, and the last one goes near the top of the rocket, which we'll talk about in a different video. I attached 4 Wago lever connectors to the lower bulkhead on the guidance package. These are going to be used to connect the explosive charges to deploy the drogue parachutes. This bulkhead also gets a big threaded rod through it with an eye nut and then a cutout for that VGA cable. After threading some pass-through leads for these charge connectors and double-checking the fit with the threaded rod, I epoxied this bulkhead in place using E120 HP, a little bit of Kevlar pulp, and some blue dye. I was pretty generous with this epoxy because it's fairly structural. Any shock loading or deployment loading that goes through this eye nut has to go through this epoxy into the sidewalls of the coupler, so I want a lot of surface area there. In contrast with the lower bulkhead, the upper one is stepped. Instead of getting sunk into the avionics package, it's just going to sit on top like a little hat. Since this whole guidance package is carbon fiber, that means it's RF opaque. RF signals can't really pass through it. So I drilled a few holes in the upper bulkhead and then wired in the GPS antenna and telemetry antenna. In my quest to fix all the problems I have with GPS and telemetry on my rockets, I'm getting a lot better at splicing coax cables. Not only splicing though, but double checking using a VNA, or Vector Network Analyzer. You can pick these things up for super cheap on Amazon, and they're really capable. I don't know why I didn't do this years and years ago, but it turns out that a lot of my problems with telemetry and GPS were just coming down to really bad antennas or really bad cable splicing. Using a VNA to check the SWR or impedance of an antenna has cleared up like 90% of my problems. It's gotten so good, in fact, that I no longer feel compelled to use these omnidirectional antennas that I used to, but instead I can go back to a ceramic patch. These are easier, they're more ubiquitous, they're cheaper, and if your rocket has roll control, it is most likely going to be looking at the same part of the sky for the whole flight, which makes the signal a little bit more stable. Moving back to cameras, these are a little bit more complicated to wire up than it might seem. This is because I'm not satisfied with simply hitting the shutter button. I need to know these cameras are recording. My livelihood is making these YouTube videos. If I have a flight and the cameras don't record, it's a big problem. To monitor this metric, I sense the current that the cameras are drawing and then use that to make a judgment as to whether they're recording or not. And to do that, I use these 0.1 ohm resistors to create a current measuring circuit. These are rated to 1.5 watts of power, which is not enough. Whoever purchased these did a bad job and purchased the wrong one. The fix is easy though. You can just chain them together in parallel, and in theory they should regulate and balance each other out. I'm like 90% sure about this, but I haven't looked it up, so fingers crossed. Anyway, that's what we're gonna do here. After double and triple and quadruple checking that the cameras were still working every step of the way, I chained 3 resistors together and wired them into the circuit. Once Ava is tied into the loop, we'll take one of the leads from the loop and put it on an analog sense pin. This will allow us to read how much current is flowing through the circuit, beam it to the ground station, and then I can make an informed decision on whether the cameras are recording or not. Moving on, before splicing together the rest of the VGA connector to the booster, I decided to label all the axes. Especially since we're doing full yaw, pitch, and roll control, we really can't mess around with any ambiguity on which axis is where. On parts of the rocket, I used a label maker, on other parts, I used a Sharpie, and I did my best to make it as clear as possible which axis was pointing in which direction. By the way, there's very little rhyme or reason to how these VGA cable wires are split up. I'm sure there's a more elegant or correct way to do this, but here's what I did. Each wire is a different color, and I fanned them all out under a top-down camera. I took a screenshot of that, brought it into a photo editor, and then started divvying things up. Once I was happy with the way things were laid out, I printed out a physical copy to reference as I was wiring things together. Before permanently tying the servos into the VGA cable, I tested each one with a servo tester. And as noted before, each servo signal pin gets wired to 2 separate pins on the VGA connector. Each one of these connections also gets heat shrunk. What's the past tense of heat shrinked? he shrunk. And then at basically every step of the way, I checked continuity religiously. I filmed quite a lot of talking segment footage here, and to be honest with you, I am not going to comb through this. Spiritually, I have not really left No Effort November. I may never leave No Effort November in my mind. Once all of the power pins are wired up, we now have this sort of tentacle spaghetti mess to deal with. Here's a 10-second timer on screen, and I want you to guess how I solved this problem. Here's a hint. It won't surprise you. It's hot glue. It's hot glue. It's always hot glue. It's never not hot glue. Using the greatest material ever, I pinned down the cables internally on the booster. When this cable gets pulled on, like when it gets pulled at apogee or if it gets tangled on the way down, I want all of that load to go through the outside of the cable. I don't want it to go through the PWM cables for the servos. That's why we're pinning it down this way, and although it does result in a unholy looking internal section, listen. We live and we learn. We listen and we don't judge. You listen to me, and I try not to judge myself. It worked, okay? It worked just fine. It looks like shit, but it worked just fine. Welcome back to the Me Justifying Bad Decisions YouTube channel. Thank you for watching. It's finally time to get a flight computer in this thing. And as I said earlier, we're gonna use the AVA flight computer, which stands for All Vehicle Avionics. It's gone through a few upgrades over the last few years, and I'll do a video on this soon, but what you need to know for now is that we're flying two computers. The white AVA is going in the nose cone, and the red AVA is for guidance. These computers are functionally identical. I just think the red looks cooler, and I want to put it in charge of cool stuff. The computer is mounted to this 3D printed sled that hangs off the bottom of the upper bulkhead. The back of the sled is flush against the carbon fiber coupler tube, which means that when we're in flight, the computer shouldn't flex around too much, which is very important if it's in charge of guidance and control. The RFD900 radio for telemetry is mounted to the right of it with a pass-through for the antenna out the top, and you're never allowed to watch a BPS video unless there's way too much hot glue used, so I put a bunch of hot glue to pot some of the electronics in there. Around this time, if you look close, you can see me get the idea that maybe I should put hot glue across the whole PCB. I am just as surprised as you are at the magnitude of stupidity with some of the decisions I make. Okay? You and I are together on this. I don't like what he's doing. Your boy dumped hot glue over the entire suite of ICs on the board. My reasoning was that I wanted no chance that any one piece of FOD could get into any metal part and cause a short or something bad to happen on the computer. But this is what silicone conformal coating is for, which I have and I could have used, but I had the hot glue in my hand. I can't even justify it. I can't even justify it. Why did he do this? Why did he do this? And then you're like, Joe, well, who cares? If it works, it works. It didn't work. It didn't work. It fried the computer. I brought AVA, the guidance package, and the booster section out to the garage and set it all up to do a little bit of integrated testing. Before I had the chance to hook up the VGA cable and start connecting the servos, I decided to do a camera test. And when I triggered the camera, I'm going to trigger the cameras and we're going to see if they put on a little light. I don't have the current sense stuff set up yet. So we're going to pull it to ground. I see some lights. Uh-oh. Shortly after triggering the cameras, seemingly for no reason, AVA power cycled. This is not a common behavior if it isn't clear, and it usually points towards some sort of power management issue. Nothing else seemed wrong with the computer though, so I kept on testing. Yeah, let's push against these. It's kind of a lot of give. With the VGA cable connected and the fins activated, I noticed that when pushing my fingers against the control tabs, they had a little bit more give than I thought they would. This doesn't have to be a total showstopper, but it does mean I have to be a little bit more careful about how I dynamically limit the max deflection that these servos can go to. I think what's happening is we're running the servo power through a lot of cabling. We're going out of the battery, into the first power switch, then into the second power switch for just the servos, then into the VGA cable, then through the VGA connector, then into the PWM cable, then all the way down the 1.5 meter length of the booster, and then into the fins, and then into the servos. That's a lot of opportunity for resistance within that long length of wire and connectors to develop, and I think that resistance probably limits the maximum torque that the servos can pull. Again, it doesn't have to be a showstopper, but this is why we do integrated testing. Anyway, then, as I kept testing, this happened. That feels kind of hot. That feels really hot. Okay, something is wrong. I wonder if it's the hot glue doing weird dielectric things. Yes, it is, you idiot. Because there's nothing else connected, so I bet it's the hot glue. Yes, it is. Okay, why don't we take the hot glue off and see if that fixes things. And if it doesn't, then we'll swap the computer and maybe the computer's bad. The computer still worked, so I brought it to the back room and then peeled off all the hot glue using a little bit of IPA to release it. When I plug the computer in now, you won't be able to feel this. Ouch, 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 ouch. Okay, so the central processor gets quite hot. Something's wrong. I mean, it will boot up, but like, you know, that's an amount of heat that is not normal. Something had shorted within the processor, but it was one of those rare failures that doesn't kill the whole thing. Ava could boot fine, but the processor just got uncomfortably hot. After swapping it for a brand new Ava that I had never coated in hot glue, everything seemed to be fine. I'm gonna power Ava on. Cool. Let's do it a couple more times. Okay, let's do it with the servos. Let's get some power surges in there. I tried as hard as I could over the course of like 20 different power-ons to replicate the issue, and I was not able to get it. I am pretty sure this confirms that it was the hot glue that caused some sort of short where there shouldn't have been one. The fix for all of this, and what I should have done in the first place to prevent FOD from shorting against anything on the board, is to use silicone conformal coating. I've used this stuff in the past. When I used to live in Tennessee in a much more humid climate, this stuff helped prevent condensation on the board from causing little shorts. If you haven't ever messed with it before, it's really cool because the stuff that I have fluoresces under ultraviolet light. This makes it a lot easier to apply. You've got to be careful about avoiding things like the barometer or the USB ports. Anything sensitive where a little bit of conformal coating can mess up the tolerances, you want to keep it out of there. But everything else can get a pretty generous coat, and then it cures under the UV. If I can present you no other reason to do this, I still think it's a good idea purely because of how cool it looks. And once you're done applying it, the computer ends up looking just about the same from a few feet away. The last step here is talking about simulation and the control system itself. This is a little bit of a tricky topic to cover because I'm not sure exactly where the line on what's okay to say and what isn't according to ITAR here, and it's also difficult to show how much work it takes to generate all of these results. That said, here's the general vibe. At the very start of this project, while I was still doing CAD, I settled in on the control tab size I want. I picked this mostly on vibes, but also with a little bit of CFD. There wasn't a specific target of control authority that I wanted to hit. I knew that I wanted more than the very, very small tabs that I had done for the roll control program in the spring, but I also knew I didn't have infinite torque available to me, so I had to hit somewhere in the middle. What I ended up doing was lots of iterative CFD to try and match the max torque spec on the servo. That's why we did all that torque spec testing in the booster video. I knew the servo had a certain amount of capability, and I designed the fin tab such that when it was at a sort of medium or medium-high deflection, we'd be close to saturating that servo's torque capability. That felt like a happy medium of having some control authority and using the servo to its fullest potential. The initial steps of CFD seem to take the most time, in my opinion. That is, setting up the mesh, making sure the results you're getting are correct, and then double-checking against other programs or other users. You can also double-check against analytical methods using things like supersonic flat plate calculations, although to be honest, I didn't really do that, and I sort of went with the vibes. This first part of CFD took about 2 weeks to dial in, and once I had results I was happy with, ironically, the second part of the CFD process was a lot longer and shorter. What I mean by that is that at the very end, I ran quite a few simulations to populate this massive spreadsheet of data that correlate the various speeds, altitudes, and deflection angles that the fins could be at. But because I had my settings dialed in, this process only took like a day and a half. Granted, that's a day and a half of constant execution from the computer, but we can do it easily and more quickly because it's just a batch run. I don't have to do anything. I don't have to babysit the computer at all. With this CFD data loaded in, I'm able to draw conclusions about what parts of it I can simplify. Many of these results end up scaling pretty well along linear trends or with polynomials. This means they can be represented in the code much easier than a massive lookup table. I can simply draw a line of best fit and say, this is pretty close, maybe within 10%, and send it. Then in the control software, when the controller says, hey, I want 5 newtons of force, we can use those polynomials or linear trends to back out what is essentially an entire datasheet of CFD data. The intermediate step here is using a program like Simulink. which I largely use to make sure that my actuators won't saturate. This is to say that I'm not trying to drive my servos at a higher bandwidth than they can operate. The final step in this process is making sure that my axes are all correct, and this is perhaps the most boring and arduous task of this entire build. Axis checks like this are me standing with the rocket, holding the flight computer in one hand, doing the right-hand rule in the other hand, and just relentlessly making sure the fin tabs move in the right direction. Ava has SITL functionality, which is software in the loop. It can trick itself into believing that it's flying and pitching around. It's not technically hardware in the loop because while there is hardware involved, like these actuators, they aren't in the loop. We don't have position feedback on them. But using all this functionality, I'm able to trick Ava into thinking it's flying and then make sure that the tabs move in the directions I want them to. I talked about this before, but I'm gonna do it again. If you're interested in getting into active control in high-powered rocketry, I would ask that you be as responsible and careful as possible. The ability to build something like this is kind of remarkable. In many countries, what I'm building here would be illegal. And it doesn't have to stay that way in the US. It could be made illegal. And the reason that would happen is if someone is really irresponsible and does something very dumb with active control in high-powered rocketry. If you're gonna do this, you've gotta do it the right way. It's very unregulated right now, and if you aren't responsible, you could be the reason that changes. So, just do your homework, make some good simulations, make good decisions, do this stuff responsibly, and that's all my advice. I have several more avionics things to talk about, but we're going to save those for later. That's all for this video. If you want to know more about what I'm doing right now and every 2 weeks for the last 2 years, I'm serious, you can get access to all those videos at once right now. That is over at $5 a month on patreon.com/BPS.space. That's how this project gets supported. I'm also turning on channel memberships here. I know some folks don't use Patreon or don't want to, and that's totally fine. So channel memberships here will get you that same thing. It's the video every 2 weeks that talks about what I'm doing in real time. Finally, before I leave y'all here, I do want to talk about the sponsor for today's video, which is Incogni. This will come as no surprise to you, but I spend a tremendous amount of time on the internet. I'm not just making YouTube videos, I'm also poking around in research papers and like weird sketchy websites with some crazy rocketry tool. And sometimes some of these sketchy websites want stuff like my email, and that stuff just ends up on the internet from time to time. I think a lot about the stuff that I'm aware of, but I think even more about the things that I'm not aware of. It's not just stuff like your email, but it's stuff like your age and your birthday and well, okay, those are kind of the same thing, but other information about you that helps these big data aggregators cobble together an image of who you are and then sell that to the highest bidder. And maybe you hear this and say, well, Joe, I don't care if people have my data. People can buy and sell whatever they want. Sure, that's fine, but it's not always people who are like above board doing this. Do you know what I mean? These lists of personal attributes about you often end up in hands that you don't want them to. The reality of being online is that this data is everywhere right now, and you won't be able to track it all down yourself unless you make it your absolute full-time job. And that is why Incogni exists. Incogni is a service that reaches out to these data brokers on your behalf to request removal of that data. Sometimes that isn't like a super smooth process, and there's a lot of back and forth, so Incogni also handles that part of it as well. One of the nice parts about Incogni is that it's always active. They're always looking for more places your data might end up, and they're always reaching out to try and delete it for you, through no effort on your part. If getting a little less online is on your 2025 resolution, Incogni is going to save you a lot of time doing that. If you want to give Incogni a shot, you can go to incogni.com/bpsincogni or use the code on screen to get 60% off an annual Incogni plan. Thanks a ton to Incogni for sponsoring this video, and thank you to you for watching. My name is Joe Barnard. May your skies be blue and your winds be low. Goodbye.